Hi, welcome back to another episode of Why My Game Isn't Done Yet. Last time, I spent 2 months modelling and animating some really cool weapon sprites, which then proceeded to break my game. Because it turns out I'd overlooked something fundamental, a pitfall that catches many amateur devs out. And if I couldn't fix it, my game Scarlet Harvest would be dead in the water before I'd even built a playable level. Confused? Let me back up. In the digital world, information is stored as bits. Bit stands for binary digit. They have only 2 possible values, 1 or 0, on or off. If you want to store colour information digitally, well then 1 bit will only allow you to store 2 possible colours, say white or black. That's enough for simple games like Pong, but not much else. If we add another bit, now we can have 4 possible colours. Space Invaders is a good example of 2-bit colour. Adding a 3rd bit lets us have 8 colours, but crucially, now we have enough for 1 bit per colour channel. 1 for red, 1 for green, and 1 for blue. That's helpful not just because many colour digital displays are made up of pixels with a red, green, and blue component, but humans' own colour vision is based on us having 3 different types of cone cell, each sensitive to a different wavelength of light. Back in the digital world, you might have seen 3-bit colour before if you ever browsed teletext or had a BBC Micro. By the time we've added 5 more bits, we're now up to 256 possible colours. IBM's VGA display controller, introduced in 1987, supported 8-bit colour and became an industry standard throughout the 1990s. So it's not surprising games from that time also featured 256 colour sprites. That includes the 2.5D shooters from which Scarlet Harvest draws some inspiration. And in the previous video, I discussed how I was processing my sprites to have 256 colours to look more akin to those games from the mid-1990s. Just one of those 256 bits is assigned to transparency, meaning pixels are either fully transparent or fully opaque. This 1-bit alpha channel introduces jagged edges and robs the image of semi-transparency. So I'd been importing my 256 colour sprites into After Effects using the original alpha channel from the Blender renders and re-exporting each sprite as a 32-bit PNG. These use 8 bits per channel, red, green, blue, and alpha, to support 16.6 million possible colours and 256 different levels of transparency. So why was that a problem? Well, let's talk about how graphics cards work. Whenever your graphics card has to load an image, be it a texture, a sprite, or a UI element, that data is first loaded into your RAM and then sent to your graphics card's video memory, or VRAM. To work out the amount of VRAM needed to store an image, you multiply its resolution by its bit depth. My weapon sprites were 1280 by 720, so that's 921,000 pixels total times 32 bits. There's 8 bits in a byte, 1024 bytes in a kilobyte, and 1024 kilobytes in a megabyte. So this one image is costing us 3.5 megabytes of VRAM to store, but I'd animated my weapons to display 15 sprites per second. Take the shotgun. It uses 56 sprites to display its fire and reload animations. All of those sprites needed to be loaded into VRAM so the engine can call them at any time. That's 196 megabytes just for this one gun. At this point, you might be asking, but wait, those shotgun sprites only take up 117 kilobytes of disk space each, how do they take up nearly 200 megabytes of VRAM? The answer is compression. Let's take this image as an example. It's 32 by 32, or 1024 pixels total. Let's assume it doesn't have an alpha channel. 8 bits for the red channel, 8 bits for the green, and 8 for blue makes a bit depth of 24 bits. If the colour information of every pixel had to be stored individually, you'd expect this image to require 3 kilobytes to store, which is certainly true when it's an uncompressed bitmap. Compression uses various techniques to reduce the amount of data that needs to be stored in an image. There are 2 types, lossy and lossless. Lossy compression discards data from the original image forever. This might involve grouping adjacent pixels together and changing their colour so the new image has fewer colours to store, as in JPEG. Or it might involve reducing the bit depth itself, limiting the number of colours an image can have, as in a GIF. The important thing to remember is that lossy compression is destructive. Once that information is gone, it can never be gotten back. Lossless compression, such as PNG, doesn't store the information for every pixel individually. The exact workings of PNG are complicated to explain and illustrate, so I've linked to an article below that explains the process in more detail. PNG uses a 2-step compression algorithm to store the difference between nearby pixels rather than their exact value. This reduces the amount of data that needs to be stored in a PNG file and therefore reduces its file size compared to other image formats. Crucially, when the image is opened, a decoding algorithm reconstructs the image perfectly, making PNG lossless. Sadly though, graphics cards need images in a format that can be opened and read instantly, so they aren't designed to work with PNGs natively. They automatically convert them to a more GPU-friendly format which stores individual pixel values again. So, regardless of what file format our image is saved in, on the GPU it will always take up 32 by 32 by 24 bits, or 3 kilobytes. All of this is a long-winded way of saying file size has no bearing on the amount of VRAM it takes to store an image. But why does all this matter? We live in an era of 24GB graphics cards and seemingly unlimited potential. Why should a few hundred PNG files cause my game to keel over? The problem is Easy FPS Editor is a 32-bit application, meaning it can only use a certain amount of RAM. Remember, every image you want to display has to be loaded into RAM first. It also doesn't help that eFPSC is not particularly efficient when it comes to memory management either. Essentially, I was running out of RAM, and once I got beyond about 1.6GB used, the engine would start having to drop sprites from memory. That's why some of my enemy sprites stopped displaying correctly. The annoying thing is, this has happened to me before. On Ignite, I had serious performance issues caused by the exact same problem. Because many of the textures were saved as 4K 32-bit PNGs, I was putting incredible stress on the RAM and GPU to hold all that information in memory. So how was I going to fix this issue? How could I reduce the memory overhead for every weapon and every enemy in the game? There were 3 possible solutions. Reduce the resolution of each sprite, reduce the number of sprites needed, or reduce the bit depth of each sprite. But it later turned out that third one isn't really an option. Other game engines support more compressed image formats like DDS, which sadly eFPSC doesn't. According to the engine's current developer, even if you feed a 256 colour PNG with an ugly 1-bit alpha channel in, the engine itself will convert these to 32-bit images at runtime. Downside, I couldn't use compression or clever file formats to save memory budget. Upside, at least I could keep my buttery anti-aliased edges. Instead, I began reanimating all the weapons to only need 10 sprites per second. It was actually easier to reanimate them at 30 frames per second, render that, and just undersample it to get more realistic movement and give me more control. But this cut the number of sprites I needed. I also reduced the resolution of each sprite. Initially I went with 960 by 540, but for most of the weapons, that leaves huge swaths of the image where nothing will ever be displayed. So I also worked out where each weapon appears on the screen and further cropped each sprite to the absolute minimum to discard even more pixels. This not only meant I had to re-crush all those new sprites, but also rewrite the finite state machines to work at a reduced frame rate. The upshot was that I managed to reduce the overhead across all the weapons from 1GB to 200MB. Using the same technique on the enemies reduced their overhead too. Finally, after much research and trial and error, I got my game working again. although it still displays a higher RAM and VRAM usage than my math says it should. The important thing is that I can finally begin working on the actual levels of this new version of Scarlet Harvest. That might take a while, so to tide you over until I have more to report, I've uploaded a new standalone to itch, the weapons test. This is your opportunity to play with 7 of the weapons I've made for Scarlet Harvest and tell me how they feel. Let me know in the comments or on itch whether they need further balancing or you spot any issues. If you enjoyed this rant about computer graphics, make sure you share this video and subscribe so you can follow my progress. Thanks for watching.